So today we are going to learn about free radicals. As we all know that free radicals are also the reactive intermediates. So free radicals are also reactive intermediates. So if I am talking about free radicals, it means that we have one electron on a particular carbon atom. So just consider these reactions. If you're going to consider some reactions, only then you are able to distinguish which reaction proceeds via free radical intermediate, which reaction proceeds via nitrogen intermediate. You have to check, like if we have 4 reactions, just suppose, you have to interpret which reaction goes by which intermediate. Either this reaction goes by carbene intermediate, this reaction go by nitrene intermediate, or it can be possible this reaction go through by carbocation and carbanion, and it might be possible that some reactions proceed by benzyne intermediates. So how you are able to distinguish either the reaction proceeds through free radical intermediate? So for that you have to consider a reaction. So we have a methane and it is reacting with the dichloride. We have a methane and it is reacting with the dichloride. This is a process in which the H is replaced by chlorine via free radical mechanism. The complete mechanism we will do in later slides. So if I have a hydrogen and that is replaced by chlorine because of the presence of the reagent, that is the 0.25 equivalent of chlorine, that is the dichlorine in the presence of light. Okay, so H is replaced by Cl. We are going to get this chloromethane. We are going to get the chloromethane, but if we have a Cl2 only, then there is no reaction. It means there is no product formation. Then the product formation usually gone through by this particular. So there is a very important role of H nu, or we can say light, or sometimes there is a chances that this triangular symbol also drawn, that is due to the heat. So it means that the reaction is governed by the heat. It means that the reaction is endothermic reaction sometimes, because we have provided the heat, and if we are going to provide the heat, it means that the reaction is endothermic reactions. So if we have provided light or heat, any one of them, and the reaction proceeds in the forward direction, it means that the reaction is taken place by free radical mechanism. So for that you have to distinguish between these two reactions. If you have a Cl2 in the presence of light or H nu, then the reaction is proceeding. But if you don't have any Cl2H2, there is no reaction, there is no product formation, and this can only be understand by the free radical intermediate reactions. So this reaction proceeds via free radical intermediate involving the initiation step, propagation step and termination step. Whereas there is no light heat, it means that there is no free radical generation, and that's why there is no product formation in this part. Now consider equilibrium does not favor an acid base reaction here in free radical. In free radical intermediate I'm talking about. So here we are talking everything in context of free radical intermediate. Now what you have to consider is equilibrium does not govern acid base reaction in the free radical intermediate. If we have a Cl minus usually act as a nucleophile. So if the nucleophile attacks hydrogen and the bonds donate on this side, there is a negative charge, and Cl, so the K equilibrium is around 10 to the power minus 58. So in the general organic chemistry, you are going to distinguish between the various reactions on the basis of the pKa values, because if the pK value is more positive, it means the acid is weaker. So it's a weaker acid, whereas it's a very, very stronger acid, and acid has the tendency to donate H plus ions, or we can say H plus hydrogen ions. So acid always has the tendency to donate the H plus ions, whereas the weaker acid acts as a base, so it usually accepts the lone pair. So base can either accepts the lone pair, or base can either accepts the hydrogen atom. So what you have to do is you have to consider the pK values as well in the radical part. So now you have to consider the second option for the Cl cleavage. So you have to consider about these curved reactions. It's a very basic thing that we have learned in the school classes, in the chemistry school classes, that the arrow movement, that is the half arrow movement for the radical formation, because in a particular bond we have two electrons, and in a particular bond if we have two electrons and we want to break the bond, so we are going to donate the bond on either of sides, that is A free radical and B free radical, because we have A and B on either sides of the bond, and if we have A and B on both the sides, on either sides of the bond, and we are going to break the bond like this, so we have to draw the single arrows in the presence of heat and light. Sometimes there is light also, but you have to consider, you have to follow the things that is present on the arrow. So you have to totally focus on the reagents present on the arrow. You don't have to assume by yourself. So don't assume by default things in the organic chemistry reactions. So everything is pre-written on the arrow part. So if everything is pre-written on the arrow part, so you have to consider this. Now next what you have to consider is, in the heterolytic cleavage we are going to show the bonds, and there we are going to form the carbocations and carbocation by the heterolytic cleavage. But here we have to do the homolytic cleavage, in which we are going to presents the free radical formation. So if you have to form the free radicals, you have to proceed via homolytic cleavage. So you have to check this. Homolytic cleavage. So now what you have to note is that each Cl ends up with one electron from Cl cell, and resulting species are free radicals, because the things are proceeds by the homolytic cleavage, because the electron distributed equally on both the atoms. Now radical stability. So if we are talking about the stability of radicals, that is most important topic in the free radical chemistry, because sometimes the questions will come in which you have to consider the stability part. So when you have to consider the stability part, what you have to proceed through, you have to first of all check the stability. So how are you going to check the stability? If I'm saying we have a methyl radical, we have a primary radical like this, we have a secondary radical, and we have a tertiary radical. Tertiary radical are more stable because these methyl groups, so what these methyl groups do, these methyl groups can show plus effect or plus H effect. That means these methyl groups are electron donating groups. So these methyl groups are electron donating. So I am saying these methyl groups are electron donating groups, and if these methyl groups are electron donating groups, they are showing positive inductive effect, positive hyperconjugation effects, and if these all inductive and the hyperconjugation effects are due to the presence of the methyl group, it means the free radical gets stabilized, because free radicals are free radicals are electron deficient species, na? So if free radicals are electron deficient species, it means it can only be stabilized by electron donating groups. And if we have electron donating group, then what you have to see, more the electron donating group attached to the free radical, more the stability is. So the stability increases in this way, because as the electron donating group increases, the stability of the free radical increases. So you have to consider these parameters. Now this can possible for the formation of carbocation and for carbanion. So if we have a dichlorion, that is the Cl, if we have a dichloride, if we have a dichloride and we have HN, that is the light. So this leads to the formation of the polar species, because this is a genuine thing in the presence of the solvent. So we will see, if we have a light and the single arrow is shown on one particular atom, it means that there is the heterolytic cleavage instead of homolytic cleavage. For homolytic cleavage, half arrow should be shown. So if we have a polar species, just consider Cl minus. Cl minus is, So Cl minus is polar species, and if we have a polar species, we would expect the reaction rates to be higher in the polar solvents. For example, we can consider water, we can consider alcohols, we can consider DMSOs, dimethyl sulfoxide, etc. Then in the non-polar solvents such as the hydrocarbons, so the significant reaction rate difference is not observed that much. So it generally implies that the neutral species which is involved in the reaction, specifically the rate limiting step of the reaction. So where there is a neutral species, that is a rate limiting step, whereas where there are polar species, that would expect the rate to be the higher in the polar solvent as compared to the non-polar solvent. So polar interactions plays a major role. So polar species acts very fast, the reaction rate is very high in the polar solvents. Now consider, this is the orbital diagram of the free radical. So if we have a free radical on near